Hey guys, in this video, I wanted to talk to you about logic ICs and glue logic. If you take a look at any schematic for microcontroller, you will be sure to eventually encounter logic gates including flip-flops, XOR gates, and multiplexers name a few. And while many people think discrete logic gates are obsolete and only have a place inside a microcontroller, I'm here to tell you that logic circuits are well suited in your modern electronics designs. When we interface discrete logic devices to a complex device like a microcontroller circuit, we call that interaction glue logic. While I will skip the introduction to logic gates, there are countless resources on such devices on the internet. I will, however, highlight some key devices you'll need to keep in your toolbox. When you look at a logic device circuits on the internet, you'll see many of them use obsolete 4000 or 7000 series logic from the 80s. While these devices were undoubtedly useful and paved the way for modern electronics, it is my view that these ancient devices have no place in modern circuits. You see, while we have always needed of functions such as ANDing, Smith triggers, and line drivers, these devices usually have high propagation delays and make them unsuitable for most designs. This does not mean that these devices don't have their place on your workbench. 30-year-old logic devices can usually be bought on a bargain and are great for prototyping. To get another reason why you should keep glue logic on hand, it is important to remember that these devices have been around for decades. In electronics, this means there are thousands of time-tested, stable designs using discrete logic out there, so we use these devices to avoid reinventing the wheel. So what type of logic ICs should you be stocking? The first device you should have is a NAND gate. A NAND gate can be configured as a NOT, AND, or AND/NOR gate. When you see one or two discrete gates, then the NAND gate is the gate you need to have on hand. So how do you go about choosing a NAND gate? Well, when searching for a modern equivalent of a device, we can of course look at every single datasheet for the devices and see the date for production. An easier method to use for indication that I have found really fails in practice is to look at the device name. If the device name is really long, then there's a good chance that it is a modern device. For example, if we want a 7000 series NAND gate we can look at the DM2400. And if we look at a data sheet, we'll see that this device was set way back in 1968. A more recent device, like the 74VCX00 MTCX, was made in 2013 and is a drop-in replacement for the original 7400 IC. Notice the device name is longer than the original, and this is a general trend you will find in logic devices. The devices with longer names tend to be more recently designed. If we look at the datasheets of these devices, we'll see that the DM2400 has a propagation delay of between 15 to 22 nanoseconds, while the modern 74VCX00 MTCX can have a propagation delay that can reach down to around 0.6 nanoseconds. Well, now you know how to find devices, and may be wondering, besides a NAND gate, is there any logic device you should keep on hand? While you won't be able to keep any 7-segment BCD device ICs, there are some devices you need to keep on hand. These include shift registers like the 748C595, octal bus transceivers like the 748CT245, and octal buffers such as the 748C240. These logic devices come in useful in many different ways. You can also keep devices similar to the 74 ALS244 line drivers, Smith triggers, and discrete flip-flops on hand, depending on what you want to do. I have found some creative ways to use some 74 ALVCH16374 3-state 16-bit edge trigger D flip-flops in some of my designs. Sometimes you need to convert from one logic level to another. For example, your PIC microcontroller may operate on 5 volts, but an LCD you may want to interface to works on 3.3 volts. A solution to this problem is to use a bidirectional logic shifter circuit using 2 MOSFETs with a couple of passives. The left MOSFET can be connected to 3.3 volts through their pull-up resistors, whereas the right MOSFET is connected to 5 volts through its pull-up resistors. This creates a way to interconnect the 3.3 volt and 5 volt logic levels. These are usually sold as 4-channel modules that you can use to prototype quickly with. Keep in mind, those such devices have limited switching speeds. Such a setup is usually good for only a few kHz, and discrete octal bus transceivers such as the 74 LVC245 will provide faster switching speeds into the megahertz range. If you find that you need a lot of glue logic to realize your design, you may consider using a small FPGA in your design. But that is a talk for another video. Thanks for watching, guys. Be sure to like and subscribe to my channel.